This is the ALU of my homebrew 8-bit CPU. It is pretty featureful already. It can do addition and subtraction, it can do left shift and right shifts, and it can do various logic operations like AND, OR, and XOR. It also has a carry flag, which is pretty handy. If you do addition and the addition overflows, you will set the carry flag and you can reuse that carry flag in the next addition. You can also use the carry for shifting. You can shift bits out of a number into the carry and then from the carry back into the number. These flags aren't just useful for computations though, they can also be pretty useful to make decisions. If you do an addition, you could check the carry flag afterwards to see if an overflow happened, and depending on the carry flag, you might decide to jump to a different part of your program to handle that overflow. Currently we only have a carry flag, but in practice we might want to have a few other flags available to make these kinds of decisions. I think it would be a good idea to go look at, for example, x86 and see what kind of flags that x86 supports and see if we can draw some inspiration from that. Okay, so it looks like on x86 there's this flags register, and that contains all the flags in the current state of the CPU. And there seem to be quite a few flags. Let me scroll down a bit. Oh yeah, that's quite a few. There's a carry flag, the parity flag, which probably tells you if the number of ones in the result was odd or even. There's an auxiliary carry, which I'm not quite sure what it does. There's a zero flag, which tells you if the result was zero. That seems useful. A sign flag, probably which tells you if the sign bit in the result was set. And then there's a trap flag, interrupt enabled, direction, not quite sure what all those do. And there's an overflow flag, which I've seen before. This seems pretty useful. I think it's mainly for sign number computation. And then there's some IO privilege level, nested tasks. This all seems to be x86 specific. And then E flags and R flags are for more modern architectures where they've added even more flags. It would be interesting to see how many of these flags are actually useful in jump instructions. So let me maybe search for x86 jump instructions. x86 jump quick reference sounds promising. It looks like in x86 you can jump based on whether the overflow flag is set or not, the sign flag is set or not, the zero flag is set or not, or the carry flag is set or not. And you can also jump based on combinations of these flags. For example, to determine if something is less than or equal, you would look at the carry flag and the zero flag at the same time, and then you can do the opposite to check if both flags are cleared. And then there are a few jumps which involve the sign flag, zero flag, and the overflow flag. And these look like they are specifically geared towards signed arithmetic, such that you can detect if a signed number overflowed when you performed an operation in the ALU. And then you can jump based on that. And then there's also a jump instruction based on the parity flag. I haven't really seen this in practice a lot, so maybe the parity flag isn't really that important. At the end of the article here, there's also this list of processor flags that are interesting for the jump instructions, and this is pretty handy. First up is the carry flag, and this we already have in my version of the ALU, so I think this is all done. The parity flag, I'm not all too sure if we really need it. We can always add it later if we really need to, so let's skip that for now. Then there is the zero flag, and this sounds pretty straightforward. The zero flag is set if the result was zero, and it is cleared otherwise. So let's go and try to add that to the breadboard. I think, first of all, we need a bit more room up here at the top of the ALU. So let me add a fresh new breadboard to make some space. All right, perfect. So that gives us plenty of room to build up what we need. Let me get rid of some of those loose wires, which we used to connect to the CPU, because we're going to replace them with new wires later on. First of all, let me add a few LEDs to show the current flags that the ALU is producing. I think eventually we'll have 4 flag bits, so let me make sure that there are 4 blue LEDs. And let me make sure the LEDs work. All good? Perfect. We'll deal with the rest of the flag register a bit later. Now, to implement that zero flag, ideally we'd want to take the 8 bits of result that the ALU produces and run those into an 8-input NOR gate. What the NOR gate would do is, if any of those bits is a 1, the output will drop to a 0, and if all of those input bits are a 0, the output will be 1. So it will basically indicate whether all of the output bits are 0, which is our zero flag. However, the largest NOR gate I can efficiently get my hands on is this 74HC 4002, which is a 4-input NOR gate. It's actually 2 4-input NOR gates. But that's not a big problem. We can just feed the lower 4 bits of the result into one of the NOR gates and the upper 4 bits of the result into the other NOR gate. And then we get 2 signals indicating whether the lower 4 bits and the upper 4 bits are 0 respectively. And then all we have to do is run that through an AND gate to compute whether the entire number was 0. So let me add that NOR gate somewhere close to the result bits. And let me hook up power and ground. And while we're at it, let me connect the power rails of the new breadboard we've added, and let me add a decoupling capacitor. Now let me connect the lower 4 bits of the result to one of the NOR gates, and the upper 4 bits of the result to the other NOR gate. Alright, that's the 8 result bits hooked up to the 4 input NOR gates. Let's give this a quick check to see if it works. That looks good. The result is 0 and the 2 LEDs are on, indicating that the lower and upper 4 bits of the result are 0. If I make any of the lower result bits a 1, the right LED turns off. And if I make any of the upper 4 bits a 1, the left LED turns off. Great, that seems to be working. To get the 0 flag for the entire result, we have to take those 2 NOR gate outputs and run them through an AND gate. This is a 74HC08 2-input AND gate. Let me connect power and ground. And now let me bring the results of the NOR gates over to one of the AND gate's inputs here. And the result of that AND gate will be our 0 flag. Going to pick the second bit here as the 0 flag. The first bit is going to be the carry flag. It's just disconnected for now. Let's see if this works. Our output is 0. And correspondingly, the 0 flag is on. That looks good. If I set one of the lower bits to 1, the 0 flag goes off. And if I set one of the upper bits to 1, the 0 flag also goes off. And the same thing if I mix a match. And when I set all the result bits to 0 again, the 0 flag turns on. Very good. So that's the 0 flag all set. Let's see what else we have. This article also mentions an overflow flag, which seems to be a bit more involved. It says that this flag is set if the result of an addition or subtraction is too large a positive number or too small a negative number to fit into the 8 bits, excluding the sign bit. So this feels like it's related to signed arithmetic. Let me see if I can dig up some more information about how this is supposed to work. This Wikipedia article on the x86 flags mentions the overflow flag. Let's see what that says. So Wikipedia here says that the overflow flag is used to indicate when an arithmetic overflow has occurred. If you're interpreting numbers as signed 2's complement numbers, the result would not fit in the bits that you have available. And they have an example here. If you add 127 to 127, you would get 254. The 254 still fits into an 8-bit register, but it has the sign bit set. So if you interpret this as a signed number, you would actually read this as the value -2, not 254. And so basically what happened is you added 127, which doesn't have the sign bit set, to 127, which also doesn't have the sign bit set, so both are positive. And the result you get looks negative. The sign bit is different than your input operands. And so Wikipedia sums this up as a negative sum of positive operands or a positive sum of negative operands is considered an overflow. So basically you're adding 2 positive numbers and the result reads negative. The article also mentions that overflow cannot occur when you're doing addition with operands of different sign or when you're doing subtraction with operands of the same sign. And it's kind of interesting here to see that subtraction is basically treated as the opposite of addition. At the end of the day, I think you can just ignore subtraction completely here, because in our ALU, what we did is we have an adder, so we just do addition, but then we negate the right-hand side input if we want to do subtraction. And this negation translates a subtraction into just an addition, where you precondition the right-hand side input to the addition. And I think this simplifies the problem quite a bit, because we can just look at the adder and its inputs, and then determine for the addition case if an overflow occurs or not. And so if we're adding 2 positive numbers and the result gets negative, or we're adding 2 negative numbers and the result becomes positive, that's the case we want to detect and where we want to set the overflow flag. The article here also mentions that internally, the overflow flag is usually generated by an exclusive OR of the internal carry into the sign bit, so the last position of the result, bit number 7, and the carry out of the sign bit. Which sounds pretty convenient, but we actually don't have the carry into the sign bit available. All we're getting from the adder chips we have is the carry out of the sign bit. Let me look for other ways how you could compute the overflow flag that doesn't involve seeing the intermediate carries. Here's an article about the 6502's overflow flag, which is probably a good starting point. Okay, so this discusses how exactly addition works and how the overflow flag works in the 6502. And the article has an interesting example table here where you can see that we're doing additions such as 80 plus 80, but then in an 8-bit signed context, this would read as minus 96, and this is what you would want to flag as an overflow. And then similarly, if you're adding minus 48 and minus 112, you'd get 96 as a result. But instead, you'd expect to see an even more negative number here. And then here's a section that describes formulas for the overflow flag. That sounds interesting. Here's the carry 6 XOR carry 7 that Wikipedia also mentioned. That's basically you're XORing the carry into and out of the sign bit, the topmost bit in your result. Here's another formula that involves the carry into the sign bit. Again, this is what we don't have available. This looks pretty complicated, but this looks promising. Overflow can be computed simply from the inputs and the result. Overflow occurs if the sign bit of the left-hand side XORed with the result is 1, and the sign bit of the right-hand side XORed with the sign bit of the result is 1. Another way to interpret the XOR gate here is the XOR gate is a 1 if the two inputs disagree, if they're not equal. So another way to read this is that you detect an overflow if the sign bits of both inputs are different from the sign bits of the result. This sounds like something we can easily build up on a breadboard. We can just take two XOR gates to do a bit of comparison between the sign bits, and we already have the AND gate, and thus we can compute the overflow flag. Let's go and try to build that up on the breadboard. I'm going to use an XOR gate to compare the sign bit of the left-hand side input to the adder with the sign bit of the result, and another XOR gate to compare the sign bit of the right-hand side with the sign bit of the result. And what the XOR gate will do is if those two bits agree, it will produce a 0, and if those two bits disagree, it will produce a 1. So that will basically give us an indication if between the left-hand side and the result and the right-hand side and the result, the sign bit flipped. So we're going to need an XOR gate for that. This is the 74HC86 chip, which has a total of 4 2-input XOR gates. Let me hook up power and ground again. Let me bring over the sign bit of the result, bit number 7, to 2 of the XOR gates over here, such that we can compare them with the left and right hand side sign bits. And the other 2 inputs of the XOR gates, we're going to connect to the left hand side sign bit and the right hand side sign bit. This is turning into quite a wiring mess. I can't wait to put this onto a PCB finally. Okay, at this stage we have 2 XOR gate outputs which indicate whether the sign bit changed between the left hand side and the result and the right hand side and the result. And to detect an overflow we want to check whether both of those bits flipped. So let me bring the output of the XOR gates over to an AND gate. And the output of that AND gate is now our overflow flag. I'm going to wire the overflow flag to the leftmost flag bit. Okay, let's see if this works. Alright, left and right hand side inputs are 0. I've selected the add operation and the result is 0 and the overflow flag is not set. That is all good because 0 is treated like a positive number and we're adding 2 positive numbers where the sign bit is cleared, and the result also has the sign bit cleared, so there was no unexpected flipping of the sign bit during the addition, so there's no overflow. Now let me make one side of the addition negative. This is the most negative number we can represent. This is minus 128. And if we add 0 and minus 128, we get minus 128 as a result. And as you can see, the overflow flag stays off. The sign bit did change between the left-hand side and the result, but it remained consistent between the right-hand side and the result. And so in essence, if you add a positive and a negative number, you'd expect to see either a negative or a positive result. And there's no combination of a positive and a negative number which would make the sign change. Same thing if I make the left-hand side negative. Minus 128 plus 0 is minus 128, and for the same reason the overflow flag stays off. The sign bit did change between the right-hand side and the result, but not between the left-hand side and the result, and so this is an expected result. You expect an addition between a negative number and a positive number to be potentially negative. Now if I make both of those numbers negative, we're now adding minus 128 and minus 128, the result is going to be minus 256, which overflows in an 8-bit adder, and it produces a 0. And as you can see, the overflow flag turns on because you're adding two negative numbers, so what you expect is that the result is also going to be negative. But due to the overflow, the sign bit flipped back to a 0, so this reads as a positive number now. This reads as 0 because of the overflow. And this is what we're detecting, since both for the left-hand side and the result, the sign bit flipped, and the right-hand side and the result, the sign bit flipped. And the same happens if we add two positive numbers. For example, we're now adding 64 plus 64, which you expect to result in the number 128. But in 2's complement arithmetic, the result is actually minus 128. The sign bit is set here. And again, the overflow flag turns on because you actually feeding a positive number to the left and the right hand side, as you can see, because of the sign bit not being set. But the result actually has its sign bit set. There's an overflow happening. And so the result of the addition here cannot be represented as a signed number. And this is what the overflow flag indicates. And this can be pretty handy if you're doing signed arithmetic to detect the overflow, because it's not as simple as looking at just the carry flag that comes out of the adder. So this is a handy flag to have in certain circumstances. That looks pretty good. Let's go look at some other flags. The only other flag that is left here is the sign flag. And this is pretty trivial. It's just the most significant bit, the sign bit of the result, which should just be a wire. Let's go and add that to the breadboard. The sign bit is actually pretty trivial to implement. We already bringing the sign bit of the result over all the way to the left to the XOR gate here. This is bit 7 of the output. And all we really want to do is to take this and wire it up to one of the flag LEDs, and thus this becomes one of the flags. Let's give that a quick try. So right now the result is 0, sign bit is off, and therefore the sign flag is also off. If I set the sign bit in the result, you can see that the sign flag goes on. That was pretty trivial. That was literally just a wire. So I think this is actually a pretty handy and fairly complete set of flags for an ALU. We have a carry flag, a 0 flag, a sign flag, and an overflow flag, all of which are fairly interesting to make decisions in a program and decide whether to skip a part of a program. Let me remove the jumper wires to the flag LEDs and let me replace them with some actual cut wires. All the way down here at the shifter, we also have a loose wire. This used to connect the carry output of the shifter down there to the carry flag. And we also want to replace this with a wire. So this gives the ALU the capability to compute those 4 flag bits from the result and some of the inputs. Now, these flags used to be directly connected to the flag register, and whenever the ALU was enabled, we would just take whatever the ALU produced as a flag output and store it in the flag register. And then we had this red LED that indicated the current state of the carry flag in the flag register, and you could use that to feed it into the ALU for an addition or some shifting. Now, one of the things about these flags, and especially if they're stored in a register, is that it's pretty difficult to set the flags to an arbitrary value. For example, what might happen is that the CPU is running, it executes an ALU instruction which produces a few flags in the flag register, but then an interrupt or an exception happens, so the CPU changes to a totally different program part, and it's basically interrupted. And if that other part of the program performs some ALU operations, which is very likely, it's going to destroy whatever's in the flag register. So for those kinds of context switches where the program is interrupted and the processor needs to do something else for a brief period of time, it must be possible to take the flags as they are, store them aside somewhere in a memory, do other operations, and then before giving the control back to the original program where it was interrupted, restore the current state of the flags. So there are 2 problems. One, you want to be able to read the current state of the flag register and store that somewhere in a regular processor register, such that you can store it to memory or do something else with it. And two, you want to be able to take a value in a general purpose register of the processor and move it back into the flags register. And with just a few ALU operations, it's almost impossible to effectively exchange these flags, for example, by carefully doing an addition or some kind of shifting to set the flags to a state that we want. And it's even more difficult to consistently read the states back out, for example, through some side effect. You could think about doing a left shift with carry to take whatever's in the carry flag and shift it into the result of the ALU, such that the carry flag becomes part of the result and you can store it somewhere in the CPU. That works for the carry flag, but some of the other flags, like 0 or overflow, are almost impossible to get into a regular processor register with just the regular ALU operations. So I think what we want to do is we want to give our ALU the ability to perform a flag swap. Basically, we want to have a special instruction that takes the current state of the flags register and produces that as the ALU result, such that it gets stored into a regular processor register. And also at the same time takes one of the inputs, probably the left-hand side, the RD operand, and stores its lower 4 bits into the flags register. And this will allow us to both read the flags if we need to, and also set the flags if we need to. And I think the easiest way to do this is to add a few multiplexers. When the ALU produces its flags as a part of the result, instead of directly storing them into the flags register, we want to put a multiplexer in front of the flags register that allows us to, in case of a flag swap, not store the current flag output from the ALU into the flag register, but just the lower 4 bits of the RD operand. And similarly, instead of directly taking the result of the adder and storing that into a register, kind of as the official result of the ALU, we can add a multiplexer where in the case of a flag swap, we don't just pass on whatever the adder produced, but instead we produce the current state of the flags register as a result, and that would then get stored into a register. So we need a 4-bit multiplexer in front of the flags register, such that we can write an arbitrary value to the flags register when we do a flag swap. And we need an 8-bit multiplexer in front of the ALU result, such that we can produce the current value in the flag register as the official result of the ALU during a flag swap. And this is actually fairly straightforward, it's just a whole bunch of wiring. First of all, let me get this flags register out of the way. Let me move it up here because we're going to use this area for the multiplexers and doing the actual swapping. Let me also add a green LED to indicate whether the flags register is currently enabled, whether it's going to update itself. Then let me connect power and ground. And let me also add a bunch of red LEDs back up here to show what the current state of the flag register is. And then let me add a few wires here that takes the 4 LEDs and brings them down here to 4 neighboring columns that we can easily connect to. Alright, now to the main event. Let me add 3 multiplexer chips that will allow us to perform this flag swap operation. I'm going to use these 74HC257 chips here. These are 2 input multiplexers, and there are 4 multiplexers in each package. These are different from some of the other 2 input multiplexers we've used in that they have a output enable signal. So these will allow us to tell the ALU to not drive its result onto whatever bus it's connected. And so instead of taking the result of the ALU and routing it through a buffer to have an output enable, we can directly control the output enable of these multiplexers and tell the ALU whether it should drive its result onto a bus or not. Let me connect power and ground of the multiplexers. These multiplexers have a select input, which tells them whether to select input 0 or input 1. And this is going to be our flag swap control signal. Let me cross-connect that input across all the multiplexers. And let me add a green LED to indicate whether the flag swapping is enabled. Alright, I think that looks good. Let's start out with the leftmost multiplexer, which is going to select what gets stored into the flags register. Let me connect the output enable of that to ground, such that the multiplexer is always enabled, because we always want to produce a value for the flags register. And now let me connect input 0 of the multiplexer to the flags that are coming out of the ALU, such that when flag swap is 0, we're just going to forward whatever the flags are that come out of the ALU into the flags register. And let me connect the outputs of those multiplexers to the flags register. Now there's also input number 1 on this multiplexer, which is what's being forwarded if the flag swap line is a 1. And we want to connect those inputs directly to the left-hand side input to the ALU, which is all the way down there in the bottom left. And this is going to be the way how we take an input coming from a register in the CPU's register file and just forward it into the flags register. Okay, so that's the flags multiplexer hooked up and connected to the input of the flags register. And at this point, let me also connect the outputs of the flag register to the red LEDs, such that we can observe what's in that register. Let's give this a quick test. I have an addition selected, and the left and right hand side are 0, so the result is 0, and correspondingly the 0 flag here produced by the ALU is set. The flags register is currently disabled, so if I toggle its clock, nothing should get stored in it. But if I enable the flags register and toggle the clock, you can see that the flags are stored in the register. Let me set the lower 4 bits of the left-hand side input. And as you can see, the result is no longer 0, and correspondingly, the 0 flag turns off. So we produce no flag bits at all, and if I toggle the clock, the flag register updates to the same value. Let me now set the flag swap signal to 1. As you can see, flag swapping is now enabled. This will make this multiplexer choose the other input and forward that to the flags register. And the other input is the lower 4 bits of the left-hand side input of the ALU. And if I toggle the clock now, you'll see these 4 bits of the left-hand side input be stored in the flags register. And there you go. And if I change the left-hand side input, and this works for any arbitrary value on the left-hand side input, we'll just take the lower 4 bits and store that in the flags register. And if I disable flag swapping again and toggle the clock, the regular flag output of the ALU will be stored in the flags register. Okay, pretty exciting, that seems to work. So now we not only have a flags register, but we can also write to it directly from a regular general purpose register of the CPU, which is a very handy thing to be able to do. Now let's do the same thing for the result of the ALU. We have these 2 multiplexer chips here providing a total of 8 bits to be multiplexed. And this multiplexer will pick between the result of the adder to be produced as the ALU's result or the current state of the flags register to be produced as the ALU's result. First of all, we want to be able to make use of the output enable of these multiplexers. So let me connect the output enable pins and let me add an LED to indicate whether they are enabled or not. The result of the ALU I want to eventually appear on the right-hand side here of this breadboard. So basically the rightmost 8 columns here should carry the result. So let me connect the outputs of these multiplexers, all 8 of them, over to this side, such that we have an easy spot here where we can plug in the rest of the CPU and take the ALU result and take it wherever it needs to go. Now when flag swapping is enabled and we're forwarding the flags register to the ALU result, we only have 4 flag register bits available, but we need to produce an 8-bit result. And I think what we want to do is we just want to set the upper 8 bits to a 0 in case we're doing a flag swap, and then the lower 4 bits will contain the flags register. So let me connect the upper 4 bits of the flag swapping input on the multiplexers to ground such that they will read as a 0. And then the other 4 bits of the flag swapping input, let me connect those to the flags register. Alright, that's input number 1, the flag swap input of the multiplexers connected. That will pick whatever happens when flag swapping is enabled. And now the only thing left to do is to take the other input, input 0, when flag swapping is disabled, from the result down here. Alright, so that's the result bits connected to input 0 of these multiplexers. Now there's one thing left to do here, There's this wire leading into the carry operation multiplexer, and this used to be connected to the current state of the carry flag in the flags register. Now all we have to do is connect this back up to the carry flag, and we happen to bring the carry flag down here, which is going to be a convenient spot to connect it to. So let me do that with an actual properly cut wire. Let's give this a quick test. Alright, we're still doing an add operation, but let me set a few bits in the left and right hand side input. So the adder does the right thing, it adds the left and right hand side and produces that result. But as you can see, the official ALU result is turned off. And in fact, this is because the output of the ALU is not enabled. When I set that output enable signal to low, such that it is active, you can see that the official result of the ALU now reflects what the adder produced. The ALU also produces a few flags, basically the sign flag, and I can toggle the clock to store that into the flags register. So with flag swapping disabled, we're just producing whatever the adder produces at the output here, and the flags register works as you would expect. But now let me enable flag swapping. And as you can see, the output of the ALU changes. We're no longer producing the adder's result as the ALU's official output, but we're taking the current state of the flags register and we're presenting that as the ALU's result. And when I toggle the clock now, you can see that the flags register updates to the lower 4 bits of what comes in from the left-hand side and not what the ALU produces as official flags. And when I change flag swapping back to 0, so regular operation, no flag swapping, you can see that the result of the ALU goes back to whatever the adder produces as a result. And when I toggle the clock, the flags register updates back to whatever the flags were that the ALU officially produced. Now, the question that remains is, how are we going to drive this flag swap signal? We've used all 8 output bits of the ALU decoder already to drive the carry, shift, and logic operation, so we don't have any spare outputs here. However, if I push the ALU up a bit, down here we have additional PLDs that implement the logic operation. And I think we have a few spare outputs down here, so let's go take a look. Let me open up the configuration file for the logic PLD, the one that implements the truth tables and the logic functions. And as you can see up here on pin 19, we do have an unused output. And I think the easiest way for us to drive this flag swap signal is to actually make it an output here in the logic PLD, because we're not using all the different truth table combinations. So we can set aside one of the truth table patterns that we're not using as kind of the flag swap pattern. So let me call this unused output flag swap. And then let's define a logic function for it. And I think the easiest thing to do here is to make the all ones truth table the special flag swap truth table. So whenever the truth table bits L0, 1, 2, and 3 are all 1, we're going to set this flag swap signal here, because this corresponds to the truth table that produces a constant 1 at the output, basically setting all the bits, and we're not really using that for anything. And the all ones pattern is also pretty easy to generate in the decoder on top of all the other patterns. So let's go for that. We're going to set flag swap if L3, 2, 1, and 0 are all 1. Let's run this through the Galette compiler and then take a look at the pinout of the chip. And that looks promising. On top of all the other inputs and outputs, we also have this new flag swap output here. So let me pull the logic PLDs out of the ALU, upload this new configuration, and then get them back in there. So that's the logic PLDs down here producing this flag swap control signal. Let's go and also update the ALU decoder, because we want to have an ALU operation that corresponds to this flag swapping. So let me open up the decoder file and let's add the new ALU operation for that. I think we just want to call this the fswap operation, and let me pick the opcode 1100 for this, so it's right up against the AND or and XOR operations. And basically we want to set the carry operation to 0, the shift operation to 0, because we don't really care about that. But then the logic operation should be 1111, the fswap operation. Let me also update the logic operation here. It's pretty simple. We just need to add another OR term where we basically check if the opcode is fswap, and if that's the case, we produce a 1. Fswap is 1, 1, 0, 0, so this will be the term f3, f2, not f1, and not f0. And we can optimize this a bit. These last two terms here differ only in f1, so we can factor out the f1 and get rid of it. And since we haven't really added any new ones to the carry operation or shift operation, they're both zeros in case we see an fswap opcode, we don't have to change anything about the disjunctive normal forms here for these outputs. So we can just leave them as they are. Let me actually copy these logic operation expressions into the .pld file, which is the actual file that we're compiling and then programming onto the PLD. Let me run this through the compiler and then pull out the decoder PLD from the ALU, and let me update the new configuration, and then let's drop it back in there. Alright, and the only thing left to do is to take the flag swap output from the logic PLD and use it to drive the flag swap signal off the multiplexers. Okay, time to give this a quick manual test. Alright, this looks good. We're adding 0 plus 0, we're producing a 0, and the 0 flag is set. And I can toggle the clock to store the 0 flag in the flags register. I can change the input such that the sign bit of the result is set, and correspondingly the sign flag is set, which I can also store into the flags register. I can produce an overflow. Adding these two numbers results in a 0, and the carry output is set. So at the flags, we can see that the carry flag is set and the 0 flag is set because the output is 0, and also the overflow flag is set because the signed addition here overflowed. And if I toggle the clock, everything gets stored into the flags register. Now let's try flag swapping. Let me select the flag swap opcode. This is the flag swap ALU opcode. And as you can see, the decoder properly decodes this into the all ones logic operation, which we've put aside to indicate flag swapping. And correspondingly, these logic PLDs set their flag swap output, and this is what drives the flag swap signal here at the multiplexers to a 1. And indeed, as a result of the ALU, you no longer see the result of the adder here, but you actually see the contents of the flags register. And if I toggle the clock, you can see that the flags register updates not to what the current flags are, but what the left-hand side input of the ALU is. You can't really see it, but the left-hand side input has the lowest bit set, basically what appears here in the flags register. And if I go back to the addition opcode, the adder does its normal thing again, and the flag swapping signal goes low again. And correspondingly, the ALU produces whatever the adder result is, and if I toggle the clock, the flags register just stores whatever the current output flags of the ALU are. This is pretty exciting. Not only do we have a lot more flags now, 4 in total, we can also do a flag swap with these multiplexers, which allows us to take whatever the left-hand side input is, store it in the flags register, and take whatever's in the flag register and produce it as the output of the ALU. And quite conveniently, with these multiplexers here, we also have an output enable signal right here in the ALU. This will come in handy when we now go and integrate this with the CPU, because we can get rid of that ALU buffer in the CPU that used to perform this job for us. So let's do exactly that. Let me get the CPU build back out, and let's integrate this, and let's see if we can make use of these new features in a program and in some new instructions. Alright, so I've gotten the CPU build back out, and I've already placed the ALU that we've just extended here on the left. I've also removed some of the jumper wires that we added during testing. And now all that's left to do is to hook these up. Let me connect power and ground back up. Then we have the clock for the flags register here, which we need to hook up to this clock wire. Then down here we have the left and right hand side inputs of the ALU. Let me connect those to the left and right hand side wires coming out of the register file. And then up here we need to plug in the ALU operation, which is coming from the instruction. Now, we used to connect the ALU result with this wire here. We used to plug this in over here at the adder of the ALU. And what this cable did is it basically took the ALU adder's result and it brought it over to the ALU buffer here. The ALU result came in at the bottom here, and then depending on whether we had the move mode enabled or the ALU mode enabled, one of those buffers down here would drive the result onto the right data bus of the register file, and then the register file would latch that in. But now we have these multiplexers here of the ALU, and the ALU itself has an output enable input. So we no longer need this ALU buffer down here. This is a function that got absorbed into these multiplexers. So instead of having this long wire all the way down here to the ALU buffer, what we can do is we can use the right data bus of the register file directly, which has a port up here that is kind of hidden, and we can connect the result of the ALU directly there. And then by setting the output enable of the ALU, we can actually tell the ALU directly whether it should drive its result onto the right data bus or whether the move buffer is enabled and the ALU shouldn't drive anything. So let me add a much shorter cable between the ALU and the right data bus. And then we can hook up the ALU's output enable directly to the output enable that used to control this buffer down here. We already have a wire for this because we used this to decide whether we should update the flags register or not. So let's just take that from there. And as before, whenever the ALU's output is enabled, we also want to enable the flag register to be updated. Alright, and at this point we no longer need this cable, the ALU result cable, because we have this direct connection up here. And we also don't need this ALU buffer down here anymore because the ALU is now capable of doing that all on its own. Let me also get rid of the LED that was attached to that buffer because the ALU has its own output enable LED. One last change I want to make is I want to be able to control whether the register file will store the data presented at the write data port or whether it will just ignore it. Currently, writing is always enabled, so whenever the RD operand of an instruction is non-zero, if it points to an actual register, we're always reading that register and also always writing that register. However, now that we have these flags in the ALU, it will be useful to sometimes do an ALU operation, but then ignore the result that comes out of the ALU and not write it back to any of the registers, and just have the ALU updates its flag register. To do this, we can use one of the enable inputs to the address decoders here that pick which registers get read or written. We've already done this for the read data port 2 of the register file, because sometimes we do want to read the data from the register on read data port 2, but sometimes we want to forward the immediate that's coming in from the instruction onto that data bus. So we have this orange wire here that's connected to one of the enables that allows us to conditionally disable reading of the read data port 2. And we can do the same thing for the write data port. Now the problem is we don't really have any spare instruction bits. All of them are used. But we currently have 4 bits of the instruction allocated for each of the register operands, but we're only using 3 of those bits right now. This is a 3-wire cable that goes over to the register address decoder because we only have 7 registers, so we don't need more than that. So I think until we have some proper instruction decoding and until we extend the register files substantially, let me take that unused bit of the RD operand and let me use that as an enable for the write data port. So whenever that bit is a 0, we are going to enable writing the registers, which is going to match the current behavior. That bit is always 0 and we're always writing to the registers. But by setting that bit to 1 explicitly, we can disable the register update. So this is instruction bit number 7. And we're going to have to make a few hops to get to where we need to go. And so that new connection here, which is basically just instruction bit number 7, will allow the instruction to control whether the register file gets updated or not. And that's all that should be needed to integrate this ALU back into the CPU. In the next episode, we're going to take a look at the instruction set architecture of the CPU and define a few new instructions that we can execute now based on the changes we've made to the ALU and based on the fact that we can now disable the write back into the register file. We're also going to update the assembler and then write a new program to test out the new instructions. And I think with the hardware features we've added today, we can actually do quite a few fancy things, and we can probably get pretty close to conditional code execution. So I can't wait to experiment with that. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.